CMC. Pharmacy courses offered: B Pharmacy, M Pharmacy and MBA. Fully Wi-Fi campus. Spacious classrooms and well-equipped labs. Digital library. Modern computer lab with internet facility. Well-qualified and experienced faculty. Professors from IITs. Understanding with MNCs for placement. Soft skill training program, seminars, workshop, cultural activities, IBM Career Education Training Partner and MOE with CMC Limited. సుదూర ప్రాంత విద్యార్థులకు బస్సు సౌకర్యం. విద్యార్థులకు వేరువేరుగా హాస్టల్ వసతి. ట్రినిటీ వ్యవస్థాపకులు. Trinity Engineering and Pharmacy Colleges, Karimnagar and Peddapalli. ఉత్తర తెలంగాణలో ఎస్ఎస్సి ఫలితాల్లో కూడా అత్యధిక గ్రేడ్లతో ట్రినిటీ స్కూల్స్ విజయ విహారం. ట్రినిటీ స్కూల్స్ 10కి 10 జీపీఏ సాధించిన వారు 95 మంది, 9.8 జీపీఏ 65 మంది, 9.7 జీపీఏ 56 మంది, 9.5 జీపీఏ 67 మంది, 9 జీపీఏ కంటే ఎక్కువ సాధించిన విద్యార్థులు 434 మంది. 100% పాస్ పర్సెంటేజ్. ట్రినిటీ మహా ప్రభంజనం.
Trinity Schools, day and residential. Special focus on IIT, medical, civil foundation, NTSC and Olympiad.
అద్భుతమైన స్వంత భవనాలలో ఆహ్లాదకరమైన వాతావరణంలో విద్యా బోధన. వెల్ ట్రాన్స్పోర్ట్ ఫెసిలిటీ అవైలబుల్ ఫర్ డే స్కాలర్స్.
Separate hostel for boys and girls. Trinity Schools.
E-powered and AC techno classrooms, day and residential. Peddapalli, Kasulapalli, Centenary Colony.
Join Trinity for success.
Today, the subject matter is viscosity, and this is a very small topic, and we can finish within. Just follow me for just next half an hour or so. Then it will be an advantage to you. Okay. Now, before getting the viscosity, let me explain you. Suppose a body, a block of this, you know from the mechanics, a block of mass m is moving on a rough surface. When a solid body of mass m of some shape is moving on a rough surface, then, as you know, this surface will exert an opposing force to the motion of the body, and this opposing force, what we call it as frictional force. So we have studied the nature of the frictional force and all that in mechanics. In very simple, that means this frictional force, what it does is it opposes the motion of the relative motion of the body. Even when the two bodies are moving one against another, so this frictional force is opposing the relative motion of the two bodies. Okay, and very similar to the frictional force in the case of the fluids. In the case of the fluids, which flow from one point to another in the space with the time. Now this fluid can be imagined. Now for the time being, imagine this is a liquid. This liquid is imagined to be consisting of several layers. This is imagined to be consisting of several layers. When the liquid is flowing, or when the fluid is flowing, the bottommost layer, this is in touch with the bed here, or the surface, the bottom surface. The velocity of this, the bottommost layer of the liquid or the fluid, is having very less velocity, ideally taken as the zero velocity. But as you are moving in the vertical direction up, the velocity of the layers goes on increasing if you move in the vertical direction. That means there is a velocity gradient along this vertical direction. That means a velocity change along the upward direction. So there exists a frictional force between every two adjacent layers. If you imagine, if you take any two layers, adjacent layers, one layer against other is exerting internal frictional forces. If you imagine, for example, if you take the three layers here, let me indicate by the arrows. The arrows also indicate the magnitude of the velocities. because we just now explained the velocity gradually increases in the y direction. So the arrows also indicate this is the envelope. You can see the velocity is increasing. And if you consider the three layers, this is the layer A, this is the layer B, this is the layer C, somewhere along the fluid flow. The layer C, the velocity of the fluid in the layer C is having more velocity compared to the layer B, in turn more compared to the velocity of the layer A. So this layer, the bottommost layer, tries to retard the upper layer. That means it exerts a frictional force on the upper layer, so retards the motion of that layer. The B layer also retards the upper layer C. So in this manner, this internal frictional forces act between every two adjacent layers. So the effect of this internal frictional force is, so therefore the fluid is retarded. That means after flowing to some extent, without, if there are no external forces or the pressures acting on this, there is no pressure difference or the external force acting on the fluid, then after going some distance it will come to halt. So these internal frictional tangential forces, these are tangential in the sense they act parallel to the layers. So these internal tangential forces acting between the layers, which are always retarding the motion of the layers, relative motion of the layers, are called as viscous forces, and the phenomenon is called viscosity. In the previous class, while we are discussing the fluid property, fluid statics, and the ideal fluid, even the fluid dynamics, in the fluid dynamics, the ideal fluid we have taken as non-viscous, that means the viscous forces are absent. But in reality, the viscous forces are always present between the two layers of a given fluid. And if you talk about the quantitative aspect of this viscous force, the viscous force is directly proportional to the area of the layer that you are talking about. The area of cross section of the layer, the bigger the area, the more frictional force acts between the layers. That is one point. And also proportional to the velocity gradient. Velocity gradient means the change in velocity in the upward direction, that is called velocity gradient. If you combine these two, what you will get is F proportional to A into dV by dy, and you can replace the proportional with a constant that is known as coefficient of viscosity. So eta is called as coefficient of viscosity, and from this you can write the formula eta is equal to F by A dV by dy. That means the tangential frictional force acting between the two layers per unit area per unit velocity gradient is known as coefficient of viscosity. The units for viscosity is in SI system, it is known as 1 Poiseuille, and in CGS system it is 1 Poise. The units are Poiseuille or Poise. 1 Poiseuille is equals to 1 Poiseuille equal to 10 Poise. This is the relation between these two. So this is the relation between these two, right? This one is the SI system, other one is in the CGS system. And the important characteristic on which, the important factors on which the eta depends. So for example, eta depends on, this is very important, eta is different for the different liquids. You can easily imagine you take a oil or the water, if you pour them on the surface, so which one is, move considerable distance. We know easily from our day-to-day life experiences, the water flows for a long enough compared to the oil, because the oil is more denser. And we can also understand the value of the coefficient of viscosity is different for the different liquids. So it depends on one word you can say is, it depends on the nature of the fluid or nature of the liquid. And the second important point is, because the fluids nothing but we are considering the liquids and gases together are considered as fluids, and the coefficient of viscosity of the liquids is much higher than the coefficient of viscosity of the gases. The gases are very less viscous compared to the liquids. And one more important point is the coefficient of viscosity depends on the density of the fluid. Depends on the density of the fluid, but it is behaving in a different manner for the liquids and gases. That means that the density increases. As the density increases for the liquids, the coefficient of viscosity increases. As the density is increasing, the coefficient of viscosity increases for the liquids, and as the density decreases, the coefficient of viscosity increases. As the density is increasing, the coefficient of viscosity behaves in a opposite manner. So coefficient of viscosity decreases for the, let me correct this one. As the density is increasing, the coefficient of viscosity for the gases is decreasing. So the gases behaves in a different manner compared to the liquids. This point you need to remember. That means the density increasing as far as the liquids are concerned. As far as the liquids are concerned, the coefficient of viscosity increases. You can understand by the previous example, water and oil and honey. So as the density is increasing, the motion of the fluid is decreases as the distance as they are progressing further, right? But in the case of the gases, as the density is increasing, the coefficient of viscosity decreases. The reason I'm not giving here, but remember in the entrance point of view, try to remember this particular information. And similarly, as the temperature increases, the temperature also has some role to play in the case of the viscous forces. As the temperature increases, the coefficient of viscosity decreases in the case of the liquids, but as the temperature increases, the coefficient of viscosity increases in the case of the gases. So these are the few important points to be remembered in the case of the liquids and the gases, especially the density and the temperature. You remember them, right? So further, let me repeat here, as the temperature increases, the coefficient of viscosity decreases for the liquids, and for the gases it increases. Now, having understood these very simple points, let us get into the one important law in this one, known as Stokes' law. So this is a very simple one and very important one as well. Suppose when this is the fluid, imagine this is the fluid. Now when an object here, when a sphere of some radius, imagine some radius, some density is there, is moving in the fluid, either horizontal direction or vertical direction, what happens is the fluid particles near to this particular solid material also dragged along with the solid body. Then there exists a viscous force between the layers of the fluid adjacent to these liquid layers or the particles, which exert a opposing viscous force on the layers, in turn on the solid body. So the motion, in nutshell, what we can say is this solid body is opposed by the viscous forces while it is moving inside the fluid. And according to the Stokes' law, I am not giving the derivation here. Dimensional, you might remember, we proved this one on the basis of the dimension analysis. But anyway, let me directly give the Stokes formula here. The formula is 6 pi eta RV. So the term 6 pi eta depends on the nature of the fluid. R is the radius of the object here. V is the velocity of this object inside the fluid. And remember, just like the frictional forces, air resistance, for example, you are moving on a bicycle or on a automobile. So as your velocity is increasing, the opposite air resistance goes on increasing. Very similar to that, as the velocity of this body is increasing, the frictional force, in this case the viscous force, is also increasing, depends on velocity. This is a very important thing. And let me explain you one important concept known as terminal velocity, denoted by Vt, when the object is dropped in a fluid. For example, a solid body of mass m and the radius r is dropped in a, this is the fluid, is imagined as several layers. Then this is dropped initially, this is dropped in the fluid. then what happens is, as I explained just now, the layers of the fluid here exert the viscous force on the body and opposes the motion of the body through it. Okay. So therefore, what force are acting? Naturally, the weight of the body, that is mg, is acting, the gravity is acting downward, as you know. And viscous forces are acting in the upward direction. Viscous forces are acting in the upward direction. Always the resistance is in the opposite to the motion of the body. And we already know we have studied in fluids, statics and all that, the buoyant force acts on the body. So now there are two forces acting in the upward direction and one force, the gravity, is acting in the downward direction. So initially, if you just look at this equation, since this is proportional velocity, initially the body velocity is less, therefore almost the frictional force is negligible, very less. Therefore, when the weight dominates the gravity dominates the buoyant force, therefore the body gets accelerated. Once the body gets accelerated, its velocity goes on increasing. Once the velocity goes on increasing, the viscous force now plays important role. That magnitude of that force goes on increasing. So the weight and the buoyant force are fixed now, but this is a variable force. That means the force increases with the velocity value. So therefore, let me write the free body diagram here. The gravity is acting down. So let me write the equation here. Fg is nothing but mg is equal to Fb. What we can write is, buoyant force is nothing but weight of the fluid displaced. What you can write is rho of the liquid and the volume of the body and g, and F is nothing but 6 pi eta RV. And this one I can write mass is nothing but the density of the solid. Let me take S, and the volume is anyway the same. The liquid displaced, the fluid displaced is same as the volume of the body. So I can write rho SVG, rho LVG is equal to what? 6 pi eta RV. So now I can write like this: 6 pi eta RV is equal to rho SVG minus rho LVG. In the beginning, out of these two terms, there is an imbalance there in the beginning. That means the velocity is quite less, but they are fixed. Therefore, you cannot write an equation in the beginning. But as the time progresses by, as the velocity is increasing, we come to a stage where the velocity as the body increases and the value of this becomes equal to the right hand side expression. So when these values balances, the net force, when this happens, the net force acting on the body is 0. When the net force acting on the body is 0, the acceleration of the body is 0, and the body moves with a constant velocity, and this constant velocity is called as terminal velocity. That is what we are going to derive an expression for that terminal velocity from this equation. So I equated them. So therefore, when I equate, I write here Vt, and the densities you can write like this. The volume, you can write the volume is 4 by 3 pi r cube, where r is the radius of the body. So let me write 6 pi eta r v t. Let me take a volume outside, that is 4 by 3 pi r cube g. Let me write here rho is the solid body density minus the liquid density. And what gets cancelled out here? 1 r you can cancel, you will get square here, and this is, you can cancel 2 3 ja, 2 4 ja, 2 2 ja. So our aim is to find out an expression for Vt. Then what you will get is pi anyway cancel out here. So 2r square g, this 3 comes down, 9, eta comes down, 9 eta into rho s minus rho l. So somehow remember this equation. It is better you have on your fingertips this formula. Somehow you, by some means, you remember the formula 2r square g by 9 eta into rho s minus rho l. So this is what the terminal velocity at a constant velocity with which it is dragged down. It will be coming down. So this in our day-to-day life also we can observe. You drop a stone, initially it moves fast, but after some time it moves very constant velocity without an acceleration. So this is how we can understand Stokes' law and terminal velocity. Now let us get into one more simple concept, as we discussed previously also, that is Reynolds number. So in the previous class also, in the fluid dynamics, we discussed Reynolds number. In the fluid dynamics, we discussed a steady flow is said to be streamlined manner. A streamlined flow means it is the streamlines are very much parallel to one another. So it looks like this is a steady flow. And when the velocity of the fluid through a pipe is increasing, this is a pipe through which the fluid is flowing, the radius is r, the diameter is d. Then as the velocity of the fluid goes on increasing, there comes a stage where this flow becomes turbulent. The streamlined flow, the steady flow, what we can say, turns into what? Turbulent. That means zigzag flow, we can say. Erratic flow or aggressive flow, we can say zigzag flow, that is known as turbulent. Beyond a certain velocity of the fluid flow, that is that velocity beyond which or at that particular velocity, streamline flow or the steady flow or the laminar flow becomes what? Turbulent flow. So that is called as critical velocity. And critical velocity depends on mainly three factors. It directly proportional to the coefficient of viscosity, it is inversely proportional to the density of the fluid, inversely proportional to the diameter of the pipe in which the tube in which it is flowing. So there are three factors on which the critical velocity depends. Combining all these, what you will get is Vc proportional to eta by rho of the fluid into diameter, not density. This is the density of the fluid and this is the diameter of the pipe in which it is flowing. And the constant of proportionality, what we call is the Reynolds number. So now in the previous class also I mentioned the formula for the Reynolds number. So that is nothing but rho VCD by eta. So this is the Reynolds number, a dimensional quantity which is only number. And I said in the previous class, if the value of this is more than 2000, the value of this is more than 2000, what you can say is the flow becomes turns into turbulent flow from the streamlined flow. So this is one concept of the what? Reynolds number. Now let us move into the one more concept, very important one. That is the Poiseuille's equation. Poiseuille's equation. So this is about the flow. That means suppose you can take a case where the fluid is moving. The fluid is moving from a point A to point B. If there is no viscous force in it, the fluid is flowing, the fluid is taken non-viscous. In this case, as the area of cross sections are same, the velocities are same, because A1 B1 equal to what? A2 V2. Because the area is same, the velocity also same. So from the Bernoulli's theorem, if you remember, I hope you remember the Bernoulli's equation, P plus half rho V square plus rho G H is constant. H is anyway for the both ends is at the same level from the ground. Rho G H has no effect. And I said V is same. So therefore the kinetic energy per unit density is also same. So therefore the pressures should be equal. Therefore P1 should be equal to P2. But in the real case, this is the case of the ideal fluid. And this is we discussed for the ideal fluid. But when the real fluid is moving, when the real fluid is flowing from end A to end B, there exists the tangential frictional forces or the viscous forces, which tries to retard the flow. Therefore, in order to maintain the flow, that means a constant velocity, in order to maintain velocity, there should be the pressure difference always across the ends. So we must apply a pressure difference to have a continuous constant flow with a velocity v. So here the pressure difference is 0 because it is considered as an ideal fluid having no viscous. Now the flow rate, the amount of fluid flowing per unit time, the flow rate can be given as A into V, the area of cross section of this pipe and the velocity with which it is flowing, that is known as flow rate, sometimes written as dq by dt, the amount of fluid flowing per unit time. Now, according to the Poiseuille's equation, I am not deriving the equation, the flow rate is given by pi r power 4 by 8 eta L, where L is the length of the pipe here, eta L, into P1 minus P2. So this is the equation given by the Poiseuille for the flow rate. And here R is the radius of this particular pipe in which it is flowing. So R is the radius, eta is the coefficient of viscosity of the fluid, L is the length of the pipe, and P1, P2, P1 minus P2. Here you can write this is pressure difference. Also you can write delta P, you can write by 8 eta L. Or sometimes this is called flow current. We call it as flow current, just like electric current or thermal current. We have seen in the thermodynamics the conduction, the current is also thermal current. In the electricity it is electric current. Here we can say it is a flow current. The flow current is nothing but dq by dt, amount of fluid flowing per unit time. And similar to those equations, we can change this equation, delta P, or the pressure difference across the ends of the tube, by 8 eta L by pi r power 4. 8 eta L by pi r power 4. Now this equation is resembling the previous Ohm's law equation. In the case of electric current, delta V by R, this R is nothing but electrical resistance. This is nothing but electrical resistance. This is the potential difference between the ends of the wire. This is electric current. In the case of the thermal current, so delta T by R, this is the thermal resistance. R equal to, if you remember, R equal to L by Ka, where K was the thermal conductivity, L and A are the physicality of the rod. So very similar, you can write now, this is where delta T is the temperature difference for the thermal flow between the ends of the rod. Here the electrical potential difference for the electric current to flow across the rod or the wire. Here we must maintain a pressure difference for the flow to happen from one end to another. And this I can write now, this is a flow resistance, where that also depends on the physicality to some extent of the pipe length and the radius. Now, so suppose the pipes are connected in series, you can say that very similar to our previous understanding, in a series of the wires, the electrical current is same, the thermal current is same, here the flow current is same. When the pipes are connected in parallel, so what is same is the pressure difference is same, the potential difference is same, or the temperature difference is same. And the resistance can be, the formula can be written as 1 by R equal to 1 by R1 plus 1 by R2. If the two pipes are in series, I can write the net flow resistance is R1 plus R2. R1 is for the first pipe, R2 is of the second pipe. So these are the some basics, basic concept of viscosity, very small concept. If you just go through this, if the question comes here, you can, easy questions comes from this one, almost based on the formula just I explained. And to show this one, let me select some of the problems here, and I will give the solution to those problems. I will explain you some problems, and then you will understand how these concepts that we are going to implement while solving the problems. Now I will take up some problems one after other. I have intentionally chosen from the previous exams. Okay. Now students, in this example, I have given one example, simple one. Just go through this question. Water from a pipe is coming at a rate of, it is coming out at a rate of 100 liter per minute. if the radius of the pipe is 5 centimeters, the Reynolds number of the flow is, the density of the water is given, and the coefficient of viscosity is also given in the information. Now students, let us see what is given here. The flow rate is given. The flow rate is given as 100 liters per minute. And just now I mentioned the flow rate can be written as A into V. So A into V is 100 liters per minute. This is one thing given. Okay. And what is next point given is the radius of the pipe is, the radius is given as 5 centimeters. You can convert this into 5 into 10 to the power of minus 2 meters. And what else is given? The density is given 10 to the power of 3. You can write 1000 kg by meter cube. And the coefficient of viscosity of the water is 1 millipoise, right? Poiseuille there. So therefore you can write 10 to the power of minus 3 poiseuilles. Okay. Now, the question is now finding out the Reynolds number. Therefore, you must know the formula for the Reynolds number, that is given by rho V D by eta. Now, the density is given straight away. The density is provided here straight away. The diameter is of course 10 centimeters. You can write 10 into 10 to the power of minus 2 meters. Coefficient of viscosity is also given there. The only point you need to find out is V. And instead of giving the velocity of the fluid, what is given is the flow rate is given. So now immediately from this AV equal to 100 liter per minute, A is nothing but you can write the cross section is, you can write circular cross section, therefore pi r square. R is given here. Into velocity we need to find out, that is given 100 liters. 1 liter is nothing but 10 to the power of minus 3 meter cube. 10 to the power of minus 3 meter cube. Minute means you can write 60 seconds. Minute means you can write 60 seconds. Now from this one, what you can write, V equals to this 100 in 10 to the power of minus 3, what you can say is 10 to the power of minus 1 by pi comes here. Let us keep pi as it is. R is nothing but, so R is nothing but 5 into 10 to the power of minus 2 square means you will get 25 into 10 to the power of minus 4 pi r square into 60. Simplify, you will get some answer here. Once you substitute in this equation, where let me simplify a little bit this one. This goes up 10 to the power of 4 becomes 10 to the power of 3. 1 cancel here, that becomes 100. And what remains is 25 into 6 here. You can write 4 and 6 there. 2 by 3. You can write, I am simplifying directly. So you will be ended with 2 by 3 pi. You can test, verify this simplification. 2 by 3 pi. Now substitute here, what you will end up with is nr equal 10 to the power of 3 is the density, and this is 2 by 3 pi, and the diameter is nothing but 10 centimeter, that means 10 into 10 to the power of minus 2 meters by coefficient of viscosity, that is 10 to the power of minus 3. So now simplify this, you will get some number here. This goes up 10 to the power of 6, 10 to the power of 7, and this is 10 to the power of 5. So therefore 10 to the power of 5, this is approximately taken 10, approximately I am finishing here. 10 to the power of 5 by 10, you will get 10 to the power of 4, you will get 2 into 10 to the power of 4. I am not sure with this number, but anyhow, my idea is how to find is the value of the Reynolds number, and the terms on the right side how to find based on the given information. So you simplify this one and will get some number for the Reynolds number. Depending on the options, you can choose one of the options. So this is given in the previous examinations. The formula is of some use now. You have to remember this formula, and the very basic concept, the flow rate, you need to remember, and you know how to convert them into meters or centimeters, SI system or CJ system. Now students, let me get into the second question after this. I hope you understood this. Okay, let me move to the second question. Students, let us get into the second question. This is a simple one related to the just now the concept we discussed, the Stokes law and terminal velocity. A solid sphere of radius r acquires a terminal velocity v1. Suppose this is a big one. When moving through the fluid, acquires a terminal constant velocity v1. The viscosity of the fluid is given eta, and this sphere is divided into what? 27 small spheres, identical solid spheres. If each of the spheres acquires a terminal speed when they are moving in the same fluid, the ratio of the V1 by V2. What are the V1, V2? V1 is the terminal velocity of the bigger sphere and V2 is the terminal velocity acquired by each of these small spheres. And immediately the very first point you need to understand is, you must know the expression for the terminal velocity. Just now I have given the equation for the information for this terminal velocity, that is given by like this: 2 by 9 r square g by eta into rho solid minus rho liquid. So this is the formula for the terminal velocity you need to employ for the given question here. And 2, 9, eta, g, all these are constants here because the liquid is same, and the density of the solid, density of the liquid also same under the given situation. The only point is, because the sizes of the spheres are varying, you can say that terminal speed is proportional to what? R square. Here, once the bigger sphere is broken into smaller sphere, what is changed is the radius is changed. The radius is changed. So therefore, I can write Vt proportional to what? R square. In the first case, when this is divided, the total volume is not changed. The total volume of the bigger sphere is equal to sum of the volumes of all the smaller spheres. So therefore, the volume of the bigger sphere, what we can take is 4 by 3 pi r cube. R I have taken the radius of the bigger one, and sum of the volumes of all these identical smaller spheres which are in 27 in number. So I can write 27 into 4 by 3 into 4 by 3 pi r cube. So let me write here, this is the bigger one r, and the smaller ones let me take here r cube, 4 by 3 pi r cube. So there you will get a relation between the radius of the bigger one and the smaller space here. 4 by 3 pi cancel out here. So r cube, what you will get is r cube, you will get 27 r cube. You can write there for r equal to 3 into r. So once you got the relation between the radio of the bigger one and the smaller spheres, I can write V1, that was the terminal velocity of the bigger sphere, is proportional to, if I take r square and let me take here r square. I suppose the small r is the radius of the smaller one, the bigger is the radius of the bigger sphere. But r I found here 3r whole square by r square. R square will get cancelled. So the ratio of the terminal velocities comes out to be 9. See, this is the all derivation, all the this question is based on one simple fact here. You need to remember the Stokes law and the terminal velocity. Now students, let me get into one more question here, one more example. So example number 3. Students, now let me explain you the third question here. What is given is 2 tubes of radii. This is one tube, the radii is given R1 and R2, and the length of this tube is given L1, and another tube is there which is of radii something R2, and the length of this tube is given L2. They are connected in series, therefore I joined end to end here, and the liquid flows through each of them in a streamlined manner. P1, P2 are the pressure differences across the ends of the tubes. That means here you can say this is the pressure difference across the end of the first tube, and you can say there is a pressure difference across the ends of the other tubes. And the relation among them is given, P2 is 4 times the P1, and the length is also given, relation L1 by 4. The question is about the radii. Here just I mentioned while explaining the Poiseuille's equation, when they are connected, what is same is, when they are connected in series, the flow current, the flow rate, or the flow current, you can say, that is constant in any series combination. This is the important point, and just I mentioned the flow current, the amount of the liquid flowing across the pipe should be equal to the amount of liquid flowing across the pipe too. And the Poiseuille's equation is you have to employ here, because this is related to the Poiseuille's equation. According to the Poiseuille's equation, the flow rate is given by, just now I mentioned here, pi r power 4 and by 8 eta L and the pressure difference. This is what I just mentioned. So this is Poiseuille's equation. And since you can apply this formula for the both cases, the flow current across the pipe 1 equal to the flow current across the pipe 2. So pi r1 power 4 by the pressure difference is given P1 here across the ends of the first tube by 8 eta. The fluid is same, the coefficient of viscosity do not change. By L1 you can write, and across the second pipe is the pressure difference P2, 8 eta L2. See what you can cancel, 8 eta can cancel, pi can be cancelled, and you need to find the relation between R2 and R1. So let me write straight away, R2 power 4 by R1 power 4 I brought here. So P1 by P2 into, you will get L2 by L1. So what is P2 given is, P2 is 4P1, therefore P1 you can only substitute the information here, and L2 is given L1 by 4. L2 is L1 by 4 by L1. So this L1 and P1 cancel, you will end up with 1 by 16. So the R2 power 4 by R1 power 4 equal to 1 by 16. You can write 2 to the power of 4 here. Therefore R2 you can write R1 by 2. So this is the final answer for the given question based on the Poiseuille's equation. So I have taken different problems related to the different concept. Just now I explained in the first half an hour. Okay, now let us move to the example 4, another question. Now let us get into the another question here. What is given? Let me read it out here. It takes 5 minutes to fill a 15 liters bucket. The capacity of the bucket is given 15 liters and the time taken to fill it is 5 minutes. From a tap of diameter is given 2 by root pi centimeters. Then the Reynolds number for the flow is what is given? The additional information, density of the water and the coefficient of viscosity also given. Now you must know the Reynolds number is rho v d by eta. So density is given, the diameter is directly given, viscosity is given, only you need to find the velocity of the flow. And what is the flow rate? The flow rate, just now I mentioned in the concept, that is can be written as A into V. That is nothing but how much is filled in how much time it is taken. So 15 liters by the time is 5 minutes. So this is what the flow rate is. So we want V actually, because to substitute here. So I can write this area, what you can write is pi r square, but the diameter is given. So this is pi r square into V. I can write 15 into 10 to the power of minus 3 centimeter cube, because this is given in centimeters. I want to keep this in centimeters. By 5 minutes, 5 into 60 seconds. And I want this V, therefore V equals to 15 into 10 to the power of minus 3 by 5 into 60. What comes down is 1 by pi r square pi. What is r square there? Diameter is given 2 by root pi, therefore radius is 1 by root pi. So 1 by root pi whole square. 1 by root pi whole square. So this is cancelled. This cancels out anyway. 5 3 ja 15, and this goes up 10 to the power of 4. It becomes 10 to the power of 4 means 3 into, I can write simplify 3 in 10 to the power of minus 3 by 6 in 10 to the power of 1 goes up. This is 3 in 10 to the power of minus 4. You can say this is 2. So I can, sorry, this is not in meter cube, this is centimeter cube. Okay, in meter cubes it is 10 to the power of minus 3, but centimeter cube, no, this is 10 to the power of 3. Okay, anyhow, this is 10 to the power of 3, 1 0 cancel here, you will end up with a square there. So what you will get is 100 by 2, you will get 50. So this is the velocity of the fluid, that is 50 centimeter per second. So once you got the velocity here, you can substitute here, but all of them are given in SI units there. We can convert this in meters here. 0.5 meter per second is the velocity of the fluid. Okay. Now, if you substitute here, rho value is given 10 to the power of 3. The velocity is given, that is 0.5. The density is nothing but 2 by root pi into 10 to the power of minus 2 meters. Let me convert into meters, but by coefficient of viscosity, that is given 10 to the power of minus 3 Poiseuille. If you substitute all this goes 10 to the power of 6. This is 10 to the power of 4. So 10 to the power of 4, this is 1 anyway. So 10 to the power of 4 by root pi. Root pi means 3.14. This you will get 10,000 by 3.14. What you will end up with approximately is, you can say nearly, this is 1.8 because 1.8 is square of this is 3.24, near to this, and if you simplify this, you will end up with the 5,400 and something like this. Approximately I am finishing, and depending on the options you can put your answer there. Maybe it is 5,500, something like this. So approximately you finish, and whichever is the nearest answer in the options, you just go for it. See here again, let me repeat the Reynolds number formula you need to know, and the very basic concept of flow rate is AV, that is indirectly given 15 liters per 5 minutes. I converted the liters into centimeter cube because R is given in centimeters. Then I convert after simplification into meters. This is the flow rate, 0.5 meter per second. Then from this velocity I found, substitute here, you will get the Reynolds number. So this is the example 4. Once you follow these examples, at least there is if the question comes in this pattern, there is every chance that you don't commit any mistake. Let me move into the next example now, example 5. Now students, let us get into the next question, number 5. The velocity of the water in a river is given 18 km per hour near the surface. That means the topmost layer, as we just understood in the viscosity, the topmost layer is having higher velocity, the bottommost layer is almost at rest. The velocity as you move upward increases gradually. Near the surface, if the river is 5 meters, the depth is also given 5 meters. Find the shearing stress between the horizontal layers of the water, and the coefficient of water is given 10 to the power of minus 2 poise. And we can convert this into Poiseuille here. I said in the beginning, 1 Poiseuille is 10 poise. So let me convert into the SI system. Therefore 1 poise is 1 by 10 Poiseuille. So this is 10 to the power of minus 3 Poiseuilles. Okay. Now anyway, coming to this one, the viscous force, what you can write is, in the very beginning we discussed dV by dx. If you take this as a surface, the river bed, this is a river bed, as you are moving up, the velocity goes on gradually increasing, and the topmost layer velocity is something given 18 kilometers per hour. You can convert this into meter per second. 1 kilometer per hour is 5 by 18 meter per second. 18 cancel, you will end up with 5 meter per second. This is the velocity of the topmost layer, and the depth of this is given h equal to 5 meters from the top surface to the river bed. Now the question is the shearing stress. The shear stress, what you can write is the F by A, the horizontal force, the tangential force acting on the layer. Of course here the viscous force I have taken by area of cross section. So what you will take now is Fe, you can take n eta A dV by dx, or dV by dy taken, because y direction let us take in the vertical manner. You can take, if you assume that is x, no problem, but generally we assume it as y. So this A gets cancelled out, you will end up with eta dV by dy. So I can take in this situation dV, I can take delta V, the velocity difference between the top and the bottom layers, and the height I can take in the place of dy, I can take the depth or the height of the river, the upper surface from the river bed. So now once you come to this one, the topmost layer velocity is 5, the bottom is 0. So the difference in the velocity is 5. 5 minus 0, 5. H is also 5. The coefficient of viscosity is given as 10 to the power of minus 3 Poiseuille. So let me substitute 5 by 5. So this cancel. So 10 to the power of minus 3, you can say Newton per meter square. So force by area, Newton per meter square. So this is the one more, based on the very basic concept of the viscosity, the question was asked. So I touched almost all the related concepts and the problems related to those concepts that I explained in the first half an hour. If you go through this session, there is every chance that, of course, you need to know, do some more problems along with this. Then only it is you will be having some advantage or edge over others. So in the next session, I will come up with another concept, the last one among these properties of matter, that is surface tension. In that session, I will explain the surface tension completely along with some more examples. Hope you understood whatever I said so far and focused very much. And thank you, and see you next time. Goodbye.
గత 3 దశాబ్దాలుగా తెలంగాణకే తలమానికంగా నిలుస్తూ ఇంటర్ ఫలితాల్లో విజయ శంఖారావం మ్రోగిస్తోన్న ట్రినిటీ విద్యా సంస్థలు ఐఐటి జేఈఈ మెయిన్స్ 2019లో ట్రినిటీ జాతీయ ర్యాంకులు, నీట్ ఎంట్రన్స్ పరీక్షలో 589 మార్కులు, ట్రినిటీ జూనియర్ కళాశాలలు. గత 3 దశాబ్దాలుగా తెలంగాణకే తలమానికంగా నిలుస్తూ ఇంటర్ ఫలితాల్లో విజయ శంఖారావం మ్రోగిస్తోన్న ట్రినిటీ విద్యా సంస్థలు ఐఐటి జేఈఈ మెయిన్స్ 2019లో ట్రినిటీ జాతీయ ర్యాంకులు, నీట్ ఎంట్రన్స్ పరీక్షలో 589 మార్కులు, ట్రినిటీ జూనియర్ కళాశాలలు. Trinity Colleges of Engineering and Technology, College of Pharmaceutical Sciences. ఉత్తర తెలంగాణలో 32 సంవత్సరాలుగా అత్యంత ఉన్నత ప్రమాణాలతో సువిశాల ప్రాంగణంలో యూనివర్సిటీ టాప్ ర్యాంకులు సాధిస్తున్న విద్యార్థులను ఉన్నత శిఖరాలకు చేరుస్తున్న ట్రినిటీ విద్యా సంస్థలు ఎంసెట్ కోడ్ కరీంనగర్ టీసీటీకే, పెద్దపల్లి టీసీఈకే, ఫార్మసీ, టీఆర్ఎన్పీ,